Electricity. The key areas covered will be electromotive force, EMF and TPD, and determining IR. What we will do today is look at the concept of electromotive force as the energy supplied to every coulomb of charge leaving the source, examine the link between the EMF and the TPD as the actual supply voltage, and determine IR using a graph. EMF and internal resistance. EMF. A source of electrical potential energy, such as a battery, provides an electromotive force, EMF. We can write this as a curly E or just a regular capital E, to drive an electron current through the circuit. The units of EMF are the same as those of potential difference, i.e. the volt, or joule per coulomb. This is a scalar. The electromotive force of the source is the electrical potential energy supplied to each coulomb of charge which passes through the source. Here's an experiment you can try. Set up a circuit as shown in the diagram. So you have a source, a bulb, a voltmeter, an ammeter, and a switch. The voltmeter is measuring the voltage across the terminals of the source, and this is the same as the voltage across the bulb. This voltage is called the terminal potential difference, written VTPD, and is the number of joules per coulomb that the battery supplies to the bulb, i.e. the number of joules per coulomb that you can put to good use. Set up the circuit as shown and record the voltage across the supply with the switch open. This is the EMF of the source. With the switch closed, record a value of the current and the new voltage. Why do you think that there is a difference in the voltages? What would happen to the current and voltage values if you added more bulbs in parallel? You can continue to add branches to the circuit and calculate the volts that are lost from your initial measurement. Fill in the following table with your values. Calculate the internal resistance of the battery for each of your data sets. Use the currents measured and the lost volts in the following equation. Internal resistance equals lost volts divided by current. Here is a second experiment. This time we have a variable resistor connected to the power supply, again using a voltmeter and an ammeter. The voltmeter is measuring the voltage across the terminals of the source, and this is the same as the voltage across R. This voltage is called the terminal potential difference and is the number of joules per coulomb that the battery supplies to the load resistance R, i.e. the number of joules per coulomb that you can put to good use. First, you set R to its maximum resistance and decrease R in steps, noting the current and voltage readings each time. Then draw a graph of voltage against current. You should have got a graph that looks something like this. So what conclusions can we draw from this? Our first conclusion is that the terminal potential difference is not constant. As current increases, the terminal potential difference decreases. This is because the cell has an internal resistance, that is given the symbol lowercase r. Energy is lost in driving the current through the chemicals that make up the cell. As the current increases, more of the available energy is lost inside the cell, and the cell gets warmer, and there is therefore less energy available to put to good use across R. Our second conclusion is that the terminal potential difference is equal to the EMF when no current is flowing, i.e. on an open circuit. When no current is taken from the power supply, no energy is wasted. Our third conclusion is that when a current does flow, the terminal potential difference is always less than the EMF. The difference between the EMF and the terminal potential difference due to the energy lost inside the cell because of its internal resistance is termed the lost volts. And we can see this in our equation. Lost volts is equal to the EMF minus the terminal potential difference. Here's a new representation of our regular circuit. Any power supply can be thought of as a source of constant EMF in series with a small resistance. So the internal resistance, we can see that just here. This is equivalent to the following circuit. Voltage divides across the small resistor and the variable resistor. So we have EMF equals the voltage across the small resistor plus the voltage across the variable resistor. So the EMF is equal to the current in the circuit multiplied by the resistance of the smaller resistor, that's the internal resistance, plus the current multiplied by the resistance of the variable resistor. If the resistance decreases, then the current increases, increasing the current multiplied by the internal resistance and decreasing the current multiplied by the resistance of the variable resistor. An important thing to note is that if the resistance of the variable resistor halves, I does not double. By conservation of energy, the energy per coulomb converted by the battery must equal the sum of the energies per coulomb converted in each of the resistors. So our EMF is equal to the potential difference across the internal resistance plus the potential difference across the variable resistor, since voltage divides in series. Therefore, our EMF is equal to the current multiplied by the internal resistance plus the current multiplied by the variable resistor resistance, since V equals IR. The potential difference across the external resistor, IR, is the same as the terminal potential difference, assuming the ammeter has no resistance, i.e., the current multiplied by the variable resistor's resistance is equal to the terminal potential difference. So overall, the EMF is equal to the current times the internal resistance plus the terminal potential difference. Here are our key equations summarized. Our terminal potential difference is equal to the EMF minus our current times our internal resistance. And our terminal potential difference is equal to the current times the load resistance. We have a couple of extra formulae that will be useful to know. To calculate the current drawn from a cell, rearrange our equation EMF equals IR plus IR. So EMF equals our current times our internal resistance plus our current times our load resistance. We can say, therefore, EMF equals our current multiplied by the sum of our resistances. And so our current equals EMF divided by the sum of our resistances. You can see this looks very similar to Ohm's law, I equals V over R. To short circuit the cell, R is set to 0 ohms. Therefore, our current in a short circuit is equal to the EMF divided by the load resistance. So that's our maximum current that we're getting there. We need to look at the equation in more detail. As the current increases, IR increases, and so the terminal potential difference decreases, assuming our EMF is constant. IR is called the lost volts. It heats up the cell. So our lost volts equation is equal to our current times our internal resistance, which is also equal to our EMF minus our terminal potential difference. Note, if our current equals 0, then our current multiplied by our internal resistance also equals 0. Therefore, our terminal potential difference is equal to our EMF. So our terminal potential difference is equal to EMF on an open circuit, so when no current flows. If we take our terminal potential difference equation, where VTPD equals E minus IR, we can rearrange this slightly. So our terminal potential difference equals minus R times I plus EMF. We can compare this to the straight line equation, Y equals mx plus c. Looking at this, Y is equivalent to our terminal potential difference. M is equivalent to minus our internal resistance. X is equivalent to the current, and C is equivalent to the EMF. Here's our graph that we can look at, and you can see that our y-intercept there, which is C, is equal to our EMF at the top left. Our gradient M is our minus R, and remembering back to maths, that's y2 take y1 over x2 take x1. And finally, our short circuit current, so the maximum current that can be drawn from the cell, is our x-axis intercept. Example 1. A car battery is connected in a circuit as shown to study how the voltage across the battery varies with the current drawn from it. For each setting of the variable resistor R, switch S is closed momentarily and the voltmeter and ammeter readings are recorded. A graph of the results is shown opposite. A. Explain why the reading on the voltmeter decreases as the ammeter reading increases. B. Use the information from the graph to find 1. The EMF of the battery, 2. The internal resistance of the battery, and 3. The current from the battery if it is short-circuited. Part A. We want to explain why the reading on the voltmeter decreases as the reading on the ammeter increases. Well, we know the voltmeter is measuring the terminal potential difference, and the terminal potential difference is equal to the EMF minus IR. So if the current increases, then IR increases. And since the EMF is constant, our terminal potential difference must decrease to keep that equation balanced. Part B. Use the information from the graph to find, first, the EMF of the battery. We know that the EMF is equal to the terminal potential difference when the current is 0. So that is our y-intercept that we're looking at here. Looking at our graph, we can see that it's a nice straight line for us to look at. If we follow the line, looking at the gradient of it, we can see that the y-intercept is at 12 volts. So our EMF is 12 volts. Part 2, we want to calculate the internal resistance of the battery. We know that the terminal potential difference is equal to minus R multiplied by I plus our EMF. And remember, comparing that to our straight line equation, y equals mx plus c. We know that the gradient of the line is equal to minus R, so R must equal minus the gradient. We want to calculate the gradient of this line. To do that, we have to do m equals y2 take away y1 over x2 take away x1. Let's pick some points to use. To make it easy for ourselves, we can take our first point to be at our y-intercept, so that would be 0, 12. And let's say our second point is at 80 and 8 there. So that's our x1, that's our y1, that's our x2, that's our y2. So we can plug those into our equation. So the gradient is equal to 8 take away 12 over 80 take away 0, and that comes out to minus 0.05. Given that R is equal to minus M, we need to take that minus 0.05 and turn it into a positive. So overall, our internal resistance is equal to, remember, minus, that's minus 0.05, which is equal to 0.05 ohms. Part 3, we were calculating the current from the battery if it is short-circuited. Remember, a short-circuited current is equal to the largest current. So that's the intersection of our x-axis this time. So having a look at our graph again, we know it's a nice straight line. We can follow that dotted line down to 240. So our current is 240 amperes. We could have gone about that a different way. We know that our short circuit current is equal to the EMF divided by our internal resistance. We just found out our EMF in part 1, that was 12, and our internal resistance, again, we just found out in part 2, that was 0.05. And that's equal to a final answer of 240 again. So you can see they both give us the same answer. Example 2. A signal generator can be considered as a source of EMF with an internal resistance. When testing loudspeakers, a signal generator with an internal resistance of 16 ohms is set to produce an EMF of 24 volts. Here's our circuit diagram. A. Find the current in the loudspeaker. B. Calculate the voltage across the loudspeaker. C. Calculate the power delivered to the loudspeaker, and D. Calculate the energy lost inside the signal generator every second. Part A, we want to find the current in the loudspeaker. To do this, we want to write down what we know and what we want to work out. We know that our EMF is 24 volts. We can see that on the diagram. The current is what we want to work out. We have an internal resistance of 16 ohms, and we have a load resistance of 32 ohms. We can plug this into our equation. Remember that our EMF is equal to our current multiplied by the sum of our resistances. So 24 is equal to I times by 16 plus 32. Expanding that out, we've got I equals 24 over 48, and that gives us a final answer of 0.5 amperes. We now want to calculate the voltage across the loudspeaker. So that's our terminal potential difference there. Our current, we already know, that's 0.5 amperes. And our resistance, that's the load resistance, that's our 32 ohms. So we know our terminal potential difference is equal to our current times our load resistance. We just need to plug those numbers in, 0.5 times 32, and we get an answer of 16 volts. For part C, we're calculating the power delivered to the loudspeaker. So remembering back to our power equations, we know we can use P equals IV, or we could use P equals I squared R. Either of these are going to get you to the same answer. So let's make a list of what we've got. Obviously, the power is what we want to work out. Our current is 0.5 amps. Our terminal potential difference is equal to 16 volts. We just worked that out. And the resistance is that 32 ohms. So first of all, using P equals IV, that's just 0.5 multiplied by 16, which gets us our 8 watts. And again, the same across at the right-hand side, P equals I squared R, 0.5 squared times 32 is equal to 8 watts. Now we want to calculate the energy lost inside the signal generator every second. So we need an equation with energy in it. It's mentioning every second, so it's going to include time. And we've just worked out power as well, so that might come in handy. An equation that links energy and time together is E equals PT, or power equals energy over time. And we know that power equals current times voltage. So combining those two equations, we have energy equals our power, IV, times by our time. Writing down what we know, our current is equal to 0.5 amperes. Our voltage, that's actually our lost volts this time because we're calculating the energy lost. Remember, lost volts is equal to current times internal resistance. And our internal resistance was 16 ohms. And we also need our time, and it's every second, so we just leave our time as 1. Combining all that, our energy lost is equal to our current times by our lost volts times by our time. So that's 0.5 times by, remember our lost volts is IR, so we need to include our current again, times by 16, that's our internal resistance, times by our time of 1, and popping that all into the calculator, that gives you an answer of 4 joules. Example 3. The circuit shown includes a cell with an EMF of 1.6 volts and an internal resistance R. The following readings are taken from the meters. The current is 0.04 amps, V1 is 1.2 volts, and V2 is 0.3 volts. A. Calculate the value of the lost volts in the circuit. B. Calculate the internal resistance R of the cell. C. The resistance of the variable resistor is altered so that the reading on the ammeter is 0.02 amps. What is the resistance of the variable resistor now? And D. The resistance R of the variable resistor is now decreased. What effect has this on the terminal potential difference of the cell? So A is asking us to calculate the value of the lost volts in the circuit, and we've got a quick reminder of those values taken as well. We know our equation is our EMF equals our terminal potential difference plus IR, and our lost volts in here is actually this IR. So rearranging this, our lost volts is equal to our EMF minus our terminal potential difference. So we know the EMF is 1.6 volts, and our terminal potential difference is something we need to calculate. Having a look at that, that's going to be the sum of our voltmeter readings. So VTPD equals V1 plus V2. Looking at our readings, that's 1.2 plus 0.3, so that's 1.5 volts. We can pop this into our lost volts equation. 1.6 minus 1.5 gets us a final answer of 0.1 volts. Now we need to calculate the internal resistance of the cell. Remembering back, our lost volts is equal to our current times our internal resistance. So we can pop our number straight into this. We just worked out our lost volts, that was 0.1. Our current is given up here, that's 0.04 amperes, and we want to multiply that by our internal resistance. Rearranging, we get internal resistance equals 0.1 over 0.04, which gives us a final answer of 2.5 ohms. The reading on the ammeter is now 0.02 amperes because the variable resistance has been altered, and that's what we want to be calculating. So let's write down what we've got. Our EMF is 1.6 volts still. Our current has been altered, that's 0.02 amps. Our internal resistance is what we just calculated, that's the 2.5 ohms. And our load resistance, we don't know, we want to calculate that, and that'll help us calculate the resistance of the variable resistor. So we have our equation, EMF equals our terminal potential difference plus IR. We can expand this out because we know our terminal potential difference is equal to I times our load resistance. And then we can write that in a bit of an easier way. So E equals IR plus R. We can pop our numbers in. So 1.6 equals 0.02 R plus 2.5. Rearranging that, we get R equals 1.6 over 0.02 minus 2.5. And that gets us an answer of 77.5 ohms. But that's not our final step. That's the total load resistance. But we just want the resistance of the variable resistor. So we can see up at the top here, we've got 30 ohms and then our variable resistor. Our resistors are in series, so all we need to do is take our 77.5 ohms and take 30 off it. So the resistance of the variable resistor equal to 77.5 minus 30, which gives us an answer of 47.5 ohms. We now need to explain what happens to the terminal potential difference of the cell if our variable resistor resistance is decreased. So looking at our equation, we know that EMF is equal to our terminal potential difference plus our lost volts, which is IR. Rearranging this for terminal potential difference, we get EMF minus our lost volts. If our resistance of our variable resistor is decreased, then our current is going to increase. And if our current increases, then our lost volts will also increase, given that our lost volts is IR. Having a look at the equation just there, if our internal resistance multiplied by our current is increasing, so if our lost volts is increasing, but our EMF is constant, which it is, then our terminal potential difference must decrease. That's our final answer. Example 4. We have a circuit set up with a resistor connected to a power supply, and we can see our internal resistance represented there. We have an EMF, a current, and the load resistance being given to us. A second 4 ohm resistor is connected in parallel with the first, and we want to find out what the new current is and what the new terminal potential difference is. Let's work out the new current first. So we want to write down what we have. Our EMF is 1.5 volts. Our current is 0.3 amps. Our load resistance is 4 ohms, but we don't know our internal resistance. And we want to find a new current, but before we are able to do that, we need to know that internal resistance. So using the initial circuit, that's circuit just with the 4 ohm resistor in, let's use our equation. EMF equals, and the format we'll use this time is current times our sum of the resistances. Plug in our numbers in, we've got 1.5 equals 0.3, and then 4 plus our internal resistance. Rearranging all that, we get R equals 1.5 over 0.3, take away 4, which gives us an answer of 1 ohm. So we know our internal resistance is 1 ohm. I'm going to add that up onto our diagram up here. So now our new current, we can work out using the same equation. Our EMF equals our current multiplied by the sum of the resistances. Our EMF is still 1.5. Our current is what we're working out. Our new resistance, again, is something we need to put in just there. And then our internal resistance is 1 ohm. So that new resistance, if we're adding on, I'll just add it onto the diagram there, adding on another resistor in parallel with the first, and that's 4 ohms, we need to use our equation for resistors in parallel. So 1 over our total resistance equals 1 over R1 plus 1 over R2. So 1 over 4 plus 1 over 4, that's equal to 2 over 4. So our total resistance equals 4 over 2, which is 2 ohms. We can pop that into our equation now. So 1.5 equals I, and then brackets 2 plus 1. Rearranging this, our current is equal to 1.5 over 3, which gives us an answer of 0.5 amps. So that's our new current. Working out the new terminal potential difference, let's think about what values we have. Our new current is 0.5 amps, and our resistance is not that 4 ohms. Remember, there was a second resistor in parallel with the first, so our new resistance was 2 ohms. That was our combined resistance in parallel. Our terminal potential difference is equal to our current multiplied by our load resistance. So that's 0.5 multiplied by 2, which gives us a final answer of 1 volt. Cells in series and parallel. If cells are placed in series, the total EMF is the sum of the individual EMFs, providing the polarity of the connections is taken into account. Example 1. 6 identical cells, each of EMF 2 volts and internal resistance 0.5 ohms, are connected in series. Part A, what is the overall EMF and internal resistance? Part B, what is the short circuit current? Thinking about part A first, we can draw ourselves a little picture to visualize it better. So remember, we don't just need to draw the cell, we can draw our resistor there to represent the internal resistance. There's our cell, we've got 6 of these connected together. So each of our internal resistances, that's 0.5 ohms. And then each of our EMFs, that's 2 volts just here. So to calculate our EMF, all we have to do is 6 times that 2 volts. So that's 12 volts altogether. And same for the internal resistance, 6 times our 0.5 amps, which is 3 ohms. For part B, we want to think about the short circuit current and think about our equation. We've got our EMF is our terminal potential difference plus our lost volts. And our short circuit current is when our terminal potential difference there is 0. So popping our numbers in, our EMF is 12, we just worked that out. The current that we're working out, and then our internal resistance is 3. Rearranging this, we get 12 over 3, which is equal to 4 amps for our short circuit current. Example 2. 4 identical cells, each of EMF 3 volts and internal resistance 1 ohm, are connected in parallel. What is the overall EMF and internal resistance, and what is the short circuit current? So we're doing the same as last time, but this time we have our circuit in parallel rather than series. So again, we can draw ourselves a little diagram of what this looks like. We have 1, 2, 3, 4 identical cells. We can split that up into their internal resistance and our cell just there. And we can label this. We've got 1 ohm for each of our resistors and 3 volts for each of the EMFs. So the overall EMF this time, thinking about our rule for voltage in parallel, the EMF we don't really need to do anything for. It's just going to be 3 volts. Voltage in parallel is the same. For our internal resistance, a little bit more complicated this time because we're in parallel, so we need to use our resistance in parallel equation. So 1 over our total resistance is equal to 1 over resistor 1 plus 1 over resistor 2, etc. So that's just 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, which is obviously equal to 4. Therefore, our total resistance is equal to 1 over 4, which is equal to 0.25 ohms. So that's part A done. Thinking about part B, the short circuit current, again, our EMF is just equal to I multiplied by the internal resistance. So that's 3 equals I multiplied by 0.25. Rearranging that, our current is equal to 3 over 0.25, which gives us a final answer of 12 amps. Example 3. We have a circuit set up here, and we need to find the current in the 5 ohm resistor, the potential difference across the 1 ohm external resistor, and the terminal potential difference of the 4 volt cell. So first of all, we're finding the current in the 5 ohm resistor. Before we start to do anything, it's very, very important to notice that these cells just here and here are facing in opposite directions. So to find our EMF, we're not adding 4 and 2, we're doing 4 take away 2 because they're in opposite directions. So that's 2 volts. If we want to find the current in the 5 ohm resistor, bearing in mind that current is the same at all points in a series circuit, and we have our EMF, we need to find the total resistance of the circuit. To do that, we first need to find our resistance in parallel, just here. So resistance in parallel, 1 over that total resistance is equal to 1 over resistor 1 plus 1 over resistor 2, so 1 over 4 plus 1 over 1, which equals 5 over 4. Therefore, our resistance in parallel equals 4 over 5, which is 0.8 ohms. We can now look at our equation EMF equals our current multiplied by the sum of our resistances. So that's 2 equals I, which is what we're trying to work out. And then looking at our internal resistance, we have 2 of those, 1 and 1.2. Adding on our load resistances, we found out the combination of those resistances in parallel, so that's plus 0.8, and finally plus that's 5 ohms just there. Rearranging that, we get current equals 2 over 1 plus 1.2 plus 0.8 plus 5, which is equal to 8, and 2 over 8 gives us an answer of 0.25 amps. Now we need to find the potential difference across the 1 ohm external resistor. So thinking about our equation, our voltage in parallel is equal to our current in parallel multiplied by the resistance in parallel, because obviously this 1 ohm external resistor is in parallel with the 4 ohm, and voltage in parallel is the same. The current we worked out for this was 0.25 amps, and the resistance that we're looking at is the combination of the 4 and the 1 ohms. So remember that was 0.8. Multiplying those together, we get an answer of 0.2 volts. Part C, we're finding the terminal potential difference of the 4-volt cell. So looking at our equation, EMF equals our terminal potential difference plus current times our internal resistance. We can start substituting our numbers in. So it's the 4-volt cell we're looking at. So 4 equals our terminal potential difference plus our current, which was 0.25, multiplied by the internal resistance. So it's still this we're looking at, so that's 1.2. Rearranging this, we get our terminal potential difference equals 4 take away 0.25 times 1.2, which gives us a final answer of 3.7 volts.